In a lot of the videos, I've been saying that it's probably going to be spontaneous or probably going to be favorable. Entropy is the other part of what makes something favorable. So you should already be able to define heat and calculate their energies, but by the end of the video, we're going to describe what entropy is, how it's measured, compare samples of entropy, calculate the entropy of a reaction using entropy of formation and Hess's law, so that way we can eventually, in our next video, talk about if the reaction is favorable and happens or not. So spontaneous reactions occur if the outside intervention is not needed. For example, if you just open up a container, the gases just happen to expand spontaneously, right? Happening on their own. It's favorable to expand. So the gas in vessel B would spontaneously fuse into vessel A, but once the gas is in both vessels, it will not spontaneously just go into one, right? So sometimes what's favorable in the forward reaction will not be favorable reverse. So spontaneous processes that are spontaneous at one temperature also might not be spontaneous at other temperatures. For example, it is spontaneous for ice to melt into regular liquid water if it's warm, but it is not spontaneous for liquid water to become ice if it's warm, right? That's only spontaneous if it's cold. So spontaneous reactions are also temperature dependent. And so we have to know like melting points and freezing points in order to determine those things. So spontaneity depends on two important issues or favorability. Entropy, which can be a measure of the randomness of a solution of a system, and the enthalpy, which is the heat of the reaction. So rusting is an example of a spontaneous exothermic process. So we said if it's exo, it's probably spontaneous or favorable. Rusting it just takes a long time. Ice melting is also spontaneous, but it's an endothermic reaction as long as it's, warm enough, right? So endo and exothermic might both be spontaneous. It depends on if this other factor of entropy. Removal of sugar from coffee is not spontaneous, right? You have to work for that. Literally work, right? Work for that. So in that case, that is not a favorable process. So the second law of thermodynamics states that the entropy of the universe increases for the second spontaneous reactions. So that's why we're saying that everything in nature tends to be more disordered. So entropy is dependent on first temperature and phase changes. Gases are the most entropic. Solids are the least because they're more ordered. The number of independently moving particles. So if you have a lot of particles, it's going to be more ways that they can arrange themselves, more what we call microstates, ways that they can be arranged. In that case, it'll be more entropic. If there's only one particle, there's only one way it can be arranged, and that is very ordered. So in that case, a solute is just one particle, maybe in the solid phase most likely, that will be very ordered, and that will be less entropy than a solution, because in that case the solute is now mixing with solution, water, or other solvent. And now that there's two different things, there's a lot of different ways that it can arrange. It may not be the solid phase anymore, it will be more aqueous or even gaseous, right? The change in phase usually has a larger effect than the number of molecules, so we're really looking at changes in phase, looking for gases. And as a last resort, polarity is also going to provide order, because remember when something is polar, they'll align themselves like poles of a magnet, plus, minus, plus, minus, plus, minus. So entropy decreases when polar molecules form. So the third law of thermodynamics, and our last law, thankfully, is that entropy of a pure crystalline substance is zero. We need something to be zero so we can compare samples, because you can't just say, hey, ice, how much randomness do you have? Like, we need some kind of scale, right? So we decided our scale would start at zero, where anything that is a pure crystalline solid at absolute zero is zero. Do we have that? No, because we don't have absolute zero. But in that case, the idea is if as at 0 degrees, it's perfectly aligned. Anything that increases temperature even 1 degree will start to shift and not be aligned, and therefore it will have some entropic value. So just like the enthalpies, entropies also have a table. The standard sign, again, means it's 1 mole at 298 Kelvin in 1 atmosphere. The units are slightly different. They're joules per mole Kelvin, and every substance has a value that's positive. So that's pretty important to look at. So they also tend to increase with increasing molar mass, because that makes it more complex. Something that is small, like hydrogen, has only a few ways it can align. Something that's larger, like CH3OH, has multiple ways it can organize, and therefore, because there's multiple ways that it can align itself, then we call it multiple microstates. That means it has more entropy. So here's an example of that. CH4 has an entropy value of 186, ethane is 229, and propane is 270 because they have more particles in there, so there's more ways that we can kind of rotate those molecules that they interact with each other. And so the entropy is increasing as you get more complex. Here's some examples. Which has a greater entropy, salt solid or salt aqueous? I hope you pick aqueous because that means there's also water. That means you have two particles which will have more different ways that it can arrange. CO2 solid versus CO2 gas. I hope you pick CO2 gas because gases have more entropy in general, and the fact that they are constantly spreading out and organizing and like reshuffling, whereas solids are very organized. They are in a geometric pattern. And then we had Ki aqueous at 45 degrees Celsius or 100 degrees Celsius. The hotter the particles, the more they move and the more kinetic energy they have. In that case, Ki at 100 degrees Celsius will have more ways it can arrange because it has more movement than 45 degrees, right? So it's really important that you know movement is associated to kinetic energy, and that because the kinetic energy is high, then the entropy is also high. You don't want to say the entropy is high because it has more movement. That's confusing entropy with kinetic. Entropy is high, it has more movement with kinetic energy, and therefore it also has more ways it can be arranged. So talk about arrangement or order when you're talking about entropy. Another way of looking at these are looking at reactions. So H2 gas and oxygen gas makes H2 a liquid. Because your phase change is going from all gaseous particles, which are completely random, to liquids that are more aligned, I'm going to say that entropy is decreasing in that reaction, it's negative. And an NH4Cl solid goes to NH3 gas and H2Cl gas because I went from a solid that's very ordered to a gas that is, roaming around and expanding at all times that necessary. I'm increasing my disorder, so I'm increasing or I have a positive S value. Like total energy and enthalpy, entropy is a state function and it depends on its final initial conditions. So we could do, to calculate it for a reaction, we can do products minus reactants like we did in the last video. So again, they can give you a reaction. This is the same reaction we did in the last video, but I'm doing it for entropy values. I also noticed that there are 4 entropy values because every substance has an entropy. There is no 0 for us. So we're going to do it the same way we did the previous video. 3 CO2s, which were valued at 213.6 each. 4 waters that were valued at 69.91 each. Subtract the reactants. C3H8 was 269.9. It only happened once. And 5 oxygens, this time this does have a value of 205, so 5 times 205. We throw it in our calculator, make sure you use these parentheses. We get negative 374.5. What that means is it's decreasing its entropy. Why? Well, before you had 6 particles of gas, and now you only have 3 particles of gas, 4 of them turned to liquids. And in that case, you've made it more ordered, so your entropy has decreased. So notice all the numbers are non-zero, the units are different, joules per mole Kelvin, so copy from the table. And this only tells us a decrease in entropy or disorder may be unfavorable, because this also depends on heat. At this point, we have to describe what entropy is, how it's measured, and compare samples, calculate the heat from standard formations, and also just so you know, this can be calculated using Hess's law or combining reactions, which we'll get to in class.